Okay, so talks about efficient algorithm for planning with participation constraints. Joint workers Cheng, who's moving to Brown as a professor, and Vincent Conitzer, who's moving to CMU as a professor. Yeah. So let me give you an overview of the talk first. So the problem we want to solve is we want to compute optimal policies in MDPs subject to participation constraints. So in this problem, we have like two parties. We have a principal who wants to compute a policy. A policy specifies an action in each state based on the state and the history. And there's also the agent who doesn't decide which action to play, but the agent has the power to leave the environment at any moment. So the problem we want to solve is we want to maximize the principal's utility while keeping the agent in the game. Right? We don't want the agent to leave. So the key difficulty in this problem is the optimal policy is sometimes necessarily randomized and history dependent. So that means, in particular, the optimal policy could be exponentially large in the flat representation in the time horizon, right? So despite that, we give a polynomial time algorithm that computes the succinct representation of the optimal policy. All right, so let's consider the following scenario. There's a customer who's negotiating a plan with a phone carrier. Right? So here's what the carrier offers. In the first year, you pay $10 per month, and after that, you pay $20. And moreover, if you quit in the first year, I'm going to charge you a one-time early termination fee, and that's going to be $100. So the customer's problem, the decision problem, is actually an MDP, right? So for example, in the first year, by the way, you don't need to remember any of this because we'll be done with that very soon. So during the first year, the MDP looked like this, right? In state now, there are two actions that the agent could play. The agent could walk away right now, sign nothing, so the termination, the procedure ends, right? Or the agent could sign the contract, pay $10, enjoy the service, and we move forward to month one. So in month one, there are again the two options. The agent could stay or the agent could quit. The difference is if the agent quits here, they pay $100. So after the first year, the MDP looks a little bit different, but the idea is the same. And another factor is over time, the customer grows more and more attached to the service. So the value of enjoying the service becomes larger and larger. So it seems difficult, but it's not so hard to solve, right? Because it's an MDP. So here's how the customer reasons about this problem. So first, the customer likes AT&T, so $10 is okay. $20 is a bit too much, right? Also, there are outside options. So if the agent, the customer, they are actually the same thing. So if the customer walks away, they can switch to, for example, T-Mobile. Those are also great carriers. And moreover, the customer definitely doesn't want to pay the $100. So maybe the most sensible policy or decision that the customer should implement is they should sign the contract right now, stay for exactly 1 year, and walk away right after that. So that's what the customer does. And after 1 year, the customer walks away. It's not the most ideal situation for the carrier. Right, so anticipating this situation, the carrier decides to offer something different. Carrier says, here's another plan. Right, you pay $15 per month. That's a flat fee, no discounts, no nothing. How about that? So that gives the agent a different MDP, a different problem to solve. Right? And here's how the customer reasons about that. $15 per month is actually reasonable in the long run. It's a fair price, but the problem is in the first several months, while the customer is still getting used to the service, the customer is probably not going to fully utilize the service, right? So in that case, the customer actually gets negative utility in the first several months. So well, in that case, maybe the more sensible thing to do is to stick to the first plan and walk away after the first year, right? So again, that's not the ideal situation for the carrier to be in. So the carrier decides to do something different again, right? So carrier's like, you know what, let's go back to the first plan. Actually, if you choose the first plan, we'll upgrade your service to 5G after the first year. How about that? Right. So now the customer's MDP is different again. So the customer's like, well, $20 per month is still a bit too much, but 5G I really like, so I'm willing to pay a little bit more for that. Right. And in that case, maybe I'll just stay within the plan even after the first year. So that's a happy ending for both the carrier and the customer. But one question remains, right? Is it really the best deal possible for the carrier? Because it's kind of random. So turns out if the carrier thinks about the problem really seriously, they'll realize that the carrier's problem is actually also an MDP, or almost an MDP. So the difference is that there are additional participation constraints in this MDP, right? Because the carrier wants the customer to never quit. So that means the customer's onward utility should be non-negative, or should be at least as good as the best outside option at any moment in the service. So this actually, I mean, sometimes maybe it's better for the carrier to just let the customer walk away, but the formulation is without loss of generality because you can quit for the customer. Well, so for example, here's how the carrier's MDP could look like. In state now, there are 3 possible actions, right? The carrier could make no change to plan, which means the customer gets 4G plus discount. In that case, the carrier's reward is medium because the discount kind of hurts the revenue. And the customer's reward is also medium because they get 4G, which is not so exciting, but they get the discount, which kind of compensates for that. Another option that the carrier could play is they could remove the discount. So this is kind of a boring action because it just moves some of the rewards from the customer to the carrier. So customer gets low, carrier gets high. And the third action, which is kind of the interesting one, is the carrier could upgrade the service to 5G right now. So in that case, the customer gets high because 5G is good, discount is good, everything's good. And the carrier still gets medium because once the infrastructure is ready, it's not really costly to upgrade one single customer. Right? So similarly, you can determine the rewards of any other state action pair. And what about policies? Like here's one policy that the carrier could implement. Right? The carrier could remove the discount in the first month and keep the plan unchanged in the second month. So this is really not an attractive policy. So most likely the customer will just walk away right now. Another thing that the carrier could do is they could make no change to the plan in the first month and then remove the discount in the second month. So in that case, the customer probably is willing to stay in the program for precisely 1 month and then quit after that. So a third policy is the carrier could upgrade the service to 5G in the first month and then remove the discount in the second month. So this is actually the most sensible policy in this graph, I guess, because customers clearly staying in the program in the first month. But after that, the discount is no longer there, but customer gets 5G, which kind of compensates the loss, so the customer is still staying. And that's the idea of this problem. Now we can get a little bit more formal. And if you are lost for whatever reason, now is a good time to come back. So here's the formal-ish definition. We have finite state space, S, which is like now, month 1, month 2, and so on. We have a finite action space, A, which is like no change, remove discount, and so on. So we have transition probabilities. P of SA and S prime is the probability that I go to state S prime when I play action A in state S. So we assume there's no cycles, which means I can only go from smaller states to larger states. So the different part from standard MDPs is we have 2 reward functions. So for example, there's the principal's reward function, RP. So that function maps every state action pair to the reward that the principal gets by playing that action in that state. And similarly, there's another reward function for the agent. So everything's similar to standard MDPs, except for the fact that we have two reward functions. So now we have a computational problem, right? Given all parameters of the environment, the transition probabilities, the reward functions, we want to compute a principal optimal policy, which maximizes the principal's long-term utility, such that the agent's onward utility in each state is at least 0, or any constant, doesn't really matter. So here we consider general policies that are history dependent. So those policies map each history state pair to a possibly random action. And the reason that we do that is, I've told you just before, is that the optimal policy generally needs to be history dependent. So we don't want to be suboptimal. And actually here's one concrete example where any history independent policy is terribly suboptimal. So this is kind of important, so I want to explain this. So let's take a look at state 2. So by definition, the agent's onward utility has to be non-negative in state 2, right? That's part of the constraint. So the tricky thing is that after leaving state 2, the agent immediately loses 1. So we have to compensate for that. Right? And the only way to compensate for that is we want to play the red action in state 4, which gives the agent 1. So that's the only thing that we can do. We can't randomize between the two actions because that's not going to be enough. Right? So say we do that, then the principal's utility in this whole thing is going to be precisely 0. It's starting. So on the other hand, if we can be history dependent, what we can do is we look at the past. If the agent came from state 2, we compensate the agent. If the agent came from state 3, we exploit the agent, which means we play the blue action that gives the principal 1 and the agent 0. So in that case, the principal's utility is precisely 0.5, which is infinitely better. Right? Okay, so I want to very quickly give you an overview of the algorithm. So the idea is that the optimal policy is huge, so we can't compute that. Right? Instead, we want to consider the Pareto frontier curves that kind of encode the optimal policy. So what are these curves? The Pareto frontier curve in state S is a mapping from each desired agent's onward utility x to the principal's maximum utility fs of x, subject to the constraint that the agent's onward utility is precisely x. So it's like, it's kind of convoluted, but it's like the best way to trade off between the agent's onward utility and the principal's onward utility. And one tricky thing here is we define these curves such that the constraints only apply in the future. They don't apply in the state S, the current state. So if we have these curves, then it's quite easy to find the value of the optimal policy, right? We just maximize this function in the initial state, and whatever we get is the value, the best value for the principal. Problem is we can't compute them because they are huge too. So instead we evaluate them. We perform two kinds of evaluations. So we evaluate the curve at the point x, which means you give me x, I give you f of x. And we evaluate the curve along a direction alpha, which means you give me alpha, I give you the farthest point on the curve along alpha. So turns out you can also pretty easily find the value of the optimal policy using these two kinds of evaluations, because you can evaluate the initial, the curve in the initial state at x equal to 0 and along alpha equal to 0, 1. So if the latter gives you some invisible point, then the former is the optimal point. Otherwise, the latter is the optimal point. So one of the two is going to be the optimal point. Okay, so how do we perform these evaluations? Suppose we want to find the green point. Then all we need to do is to find the blue and the green points, because the green point is a convex combination of the two, right? So how do we find the blue point? Observe that there's a direction, the blue direction, such that if we query along that direction, we're going to get the blue point, right? So we just want to find that direction. How to find that direction? We binary search over the direction, make many queries along directions, right? So until one of them gives us precisely the blue point. So the point here is one query at a point reduces to many queries along directions. And a central issue is numerical precision, which I don't want to explain. So what about evaluations along directions? Say we want to evaluate the curve along a direction alpha. What does that mean? That means we want to find the optimal policy from the state S with alpha as the objective direction, right? So here's why we want the curve to be unconstrained in S, because if the policy is unconstrained in S, then we know that the sub-policies also must optimize along the direction alpha, right? So we just find those sub-policies. The way that we find those sub-policies is just we make more queries in later states, right? So to find the sub-policy in S prime, we just make 2 queries in S prime, and that's it. So the bottom line here is that one query along a direction reduces to many queries in the future. So there's no, let me say, cycles in those queries. So now we can kind of perform these evaluations. Because there's no cycles, we can just recursively evaluate the frontier curves. It's going to terminate in finite time, right? But it's generally exponentially many queries. But turns out there's a way to schedule these queries in a global way, in a kind of backward induction-ish manner. So we only have polynomially many evaluations. And the numerical issue works out, everything works out, that's it. I want to briefly mention one future direction because, in particular, because Brian just told us everything about solving extensor form games, finding correlated equilibria. So one very interesting direction is how can we combine the techniques of this paper with techniques for solving correlated equilibria in extensor form games, right? Because, equilibrium computation in extensor form games are, it's very well studied, but most results are about the tree form. So if we reach a state in 2 different ways, that's like 2 nodes in the game tree. But this problem, like MDPs, they are graph form, right? It doesn't really matter how you reach a state is a state. So the hope is maybe by combining the techniques in this paper and known techniques for extensor form games, we can get some results for equilibrium computation in the graph form, which would be really interesting. And maybe I can also mention this. So another variant of the problem is if you look at the problem from a maximum design angle, then we are pretty much solving a dynamic maximum design problem with individual rationality only, right? That's the participation constraints. So we want the utility to be non-negative, but nothing else. What if the agent can misreport too? So in that case, we have a full-blown dynamic maximum design problem where we also want to be incident compatible. So it turns out that problem is interesting too. So for example, we, actually a subset of the authors, have this paper where we answer the question, the computational question of planning with both IC and IR constraints. So the answer is in long horizon environments, the problem is APX hard. And in short horizon environments, you can solve the problem using some complicated LP. And that's it.
All right. Thank you.
Yep.
So we have time for a question or 2. So does anyone have any questions?
So in your definition of the participation constraint, do you, for the value of the agent, is it the expected reward or the realized reward?
It's expectation over the realization in the future, but it's conditioning on the realization in the past. Does that answer your question?
Yeah. A follow-up question is, in your definition of this fx, this function, what if, is it defined for all possible x? I mean, for, say, all x on the real line, or only some achievable rewards?
Good question. So I kind of admitted that in the talk. So there's a non-trivial domain, but that domain you can show it's as a continuous interval on the real line. So that's fine.
So that means do you add some additional structure on the MDP transition or to make it?
No, you don't need that. So the reason that it's an interval is like take any 2 points, you can combine them by randomizing and get any point in between, right?
Okay, great. So I guess everyone's probably ready to eat dinner. So let's thank all the speakers again, and let's go to dinner.